In this problem, we're going to take a look at how we can use integration and integral calculus to help us solve some problems involving motion. So I'm going to use my example of a car here traveling along the ground. And we're going to say, for sake of argument, that its velocity versus time graph, or velocity versus time equation, is t cubed. And we'll just say it's meters per second here. There actually is a slight unit problem here, but we'll ignore that for now because it's actually seconds cubed. But all right, and what we want to find is how far the object travels. It's changed its position, and the time interval 1 second to t equals 3 seconds. So for a 2-second time frame, how far does the object travel? So along with the picture here of the car, I want to have you draw some mini graphs. We have a little x versus t graph here. And we have velocity versus time. And these graphs may differ depending on the type of integral we're using or the type of problem, but for this one, these are the three we're going to use. So it's acceleration versus time. And what we're given is this guy, so just t cubed, something like that. And we're interested in the change in position from 1 second to 3 seconds. So if I look at this graph here, it's this 1 to 3 second time frame, 2 second. So we want information about this graph. So if we know the velocity versus time graph, to get the position, we need to find the area under the curve or integrate. We need to find this area here. Okay. So step one, we say, what's the general statement? X is equal to the integral of v of t dt. Okay. Indefinite. Step two, the variables. Well, the variables are, let's see, the position versus time, which we don't know, and the velocity versus time, which we do know, x of t, which is t cubed meters per second. And then step three, solve. We have to perform the integration. So it's a three-step process. We'll step part A, B, and C. Okay. So A is, let's see, we write it as x of t is equal to the integral of v of t dt, and then specifically it's equal to the integral of from 1 to 3 of t cubed dt. Okay. Step B is we actually perform the integration, so this looks like a t to the 4th over 4 from 1 to 3. And then lastly, step C, we actually perform it. So this looks like t to the 4th over 4 minus 1 to the 4th over 4. And this looks like 81 fourths minus 1 fourth. That equals 80 over 4, which works out 80 over 4, which works out to 20. And we'll use meters here. So the answer is 20. So that's our final answer. But up here, what are we doing here? So this looks like the area. This area is 20. That's the area under the curve. So what's that got to do with this graph? Well, this graph is a t to the 4th. So I'll just kind of skip to t to the 4th, something like that. So between this 1 and time equals 3, looks like we have this change here. This change in position is 20. So in that 1 second time frame, it changes a position of 20 meters, which is the area under this graph. So we can get a graphical representation of what we're doing and what area we're solving for, what it means to the graph above it. So for integral calc type problems, we're going to have a given with some mini sketches. Find. We list our integral, list our variables or equations. Step A, rewrite the integral with the correct equation, integrate, and then solve for our limits. We got our answer. And then try to relate that to back to the graphs that we drew back in the beginning. So those are the steps for an integral calc type problem.